This is the second 6.1 video where we're going to look at continuous random variables. So remember, a continuous random variable is a variable that takes all the values in an interval of numbers. So discrete, we could list all the outcomes, 0, 1, 2, 3. Continuous, there is an interval and it could take any value in that interval. Let's jump down to our first example. Here we're going to use the probability distribution of a continuous random variable for a uniform or normal distribution to calculate the probability of an event. Let's look at a uniform example first. Selena works at a bookstore in the Denver International Airport. She takes the airport train from the main terminal to get to work each day. The airport just opened a new walkway that would allow Selena to get from the main terminal to the bookstore in 4 minutes. She wonders if it will be faster to walk or to take the train. Let y equal Selena's journey time to work in minutes by train on a randomly selected day. So that's the random variable that they've defined. Y is going to represent her travel time on a randomly selected day. The probability distribution of y can be modeled by a uniform density curve on the interval from 2 to 5 minutes. Find the probability that it will be quicker for Selena to take the train than to walk that day. So first, let's draw a density curve to represent this. And if I haven't said this yet, continuous random variables are represented by density curves. So here is the density curve, and a couple of things to remember about a density curve. Density curves are always above the horizontal axis, like you've seen. This one is uniform because it's even across every value. It's even across, and density curves always have an area of 1. So I know that the area of this box you see here has to be 1 if it's a density curve. So if the distance is 1, 2, 3, the base has a width of 3. That means the height has to be 1/3 because 3 times 1/3 gives you 1. So she can take the train or she can walk. Now, the new walkway says that it will take her 4 minutes to walk, and they want to know what's the probability that it's quicker for her to take the train. So it's only going to be quicker if the train gets her there under 4 minutes. So y is the distribution of her train times on a randomly selected day. So we want to find the probability that y is less than 4. To find the probability of her having a time less than 4 when she takes the train, we always use the area to find the density curve. So less than 4 will be this shaded region here. So we have a base of 2 and a height of 1/3. So to find the probability of y being less than 4, we'll multiply 2 times 1/3. So the probability of the train being quicker is 0.667. That means there is a 66.7% chance that she'll arrive there quicker with the train on a randomly selected day. Probably it would be quicker to take the train on a randomly selected day is 0.667. So remember, this is a uniform density curve, and we find probabilities by calculating the area underneath the density curve. This is the probability of her time being less than 4. The next example we're going to look at is, instead of a uniform density curve, we're going to look again at a normal distribution. So the heights of young women can be modeled with a normal distribution that has a mean of 64 inches and a standard deviation of 2.7 inches. Suppose we choose a young woman at random. Let y represent her height in inches. So what type of variable is y? Is it discrete or is it continuous? And this is going to be a continuous random variable because there's an infinite amount of heights that could be selected between the interval from the smallest height to the largest height. So continuous random variables, we cannot list out all of the possible options. There are gaps in discrete, but there are not in continuous random variables. Again, it's continuous because you're selecting a number between, or any number in an interval of heights. Other types of continuous random variables would be if you were measuring the weight of something, or if you were measuring race times, because there's an infinite amount of outcomes for those different types of variables. So this is going to jump back to normal distributions, which we've worked with before, but now we're just applying them to a random variable. So now we have a letter here to represent the height of a randomly selected young woman. So let's draw out the density curve for the distributions of heights, and then we'll calculate the probability of randomly selecting somebody that is less than or equal to 63. So this is what the density curve would look like, centered at 64, and I could draw my 3 standard deviations above and 3 standard deviations below. We want to find the area, which will tell us the probability of getting a height that is less than or equal to 63. So 63 is going to be below the mean, and I'm going to find the area of this shaded region using a normal calculation statement. So hopefully remember, in my normal calculation, I have to list my lower, which is negative infinity because there's nothing stopping it. Upper is 63, that's the top of the region. Mean is 64, standard deviation is 2.7. I'll open up my calculator to refresh on how to put this in the calculator. We're going to hit second vars, which takes us to normal, or to distributions. Scroll down to normal CDF. We always use CDF, not PDF. CDF is cumulative. So our lower, we said, was negative infinity. That will suffice for negative infinity. You could just do negative 999,000. Upper, we said, was 63. The mean is 64, and the standard deviation is 2.7. So if you don't have the wizard like I just had there, then you're going to have to actually type it in with your commas separating each of these values. Hit enter. So the probability is 0.3556. And so the probability transferred from the calculator is 0.3556. Interpreting what this means, the probability that a randomly selected young woman has a height less than 63 inches is about 0.3556. So one thing I want to make sure I have said here is that this says y is less than or equal to 63. But if I said instead the probability of y being less than 63, although these two statements appear to be different, these are both going to give you the exact same probability. And the reason why is because these are both calculated based off of the area of this density curve. And so if I include 63 or I do not include 63, this distance is infinitely small, and it doesn't change the area of this region here. So including 63 or not including 63 gives you the same probability. So I see students all the time, they say, since it's less than 63, then in their calculator, they go from negative infinity up to 62.99999. But in reality, if it's less than, you're still going to put 63 as your upper cutoff, because the areas are going to be the same. So now let's find the probability of randomly selecting a young woman and her height being greater than or equal to 68 or less than or equal to 70. So I'll sketch a picture, and then I'll write out my normal calculator statement. So I've drawn my normal curve centered at 64 with a standard deviation of 2.7. I want to find the shaded region between 68 and 70. So here's my lower cutoff and my upper cutoff. And if I type this into my calculator like I did in the previous problem, now I don't have a negative or a positive infinity because I have two bounds here. It stops at 68 and 70. Put that in the calculator, I'm going to get 0.0561, which means the probability that a randomly selected young woman has a height between 68 and 70 inches is about 0.0561. So moving forward with problems like this, we can only use the normal density curve if they've told us in there somehow that the distribution is normal. So be aware of that. Go ahead and take a look at the independent practice problems. There could be some discrete and continuous problems in there. Go ahead and solve them and check your work.